This is the lecture for Module 2 of Unit 5. Unit 5 is the unit on acids and bases. Module 2 concerns the pH of weak acids and weak bases. Now we saw in the previous unit that it is fairly straightforward to calculate the pH and the pOH and concentrations of H+ and OH in solutions of strong acids and strong bases. The matter of dealing with weak acids and bases is a little more complicated, and we will begin to discuss it here. First, remember which acids are the strong and which are the weak. Review strong acids. The strong acids you're supposed to know are HCl, HBr, HI, HClO4, and HNO3. You also know sulfuric acid, H2SO4, is a strong acid. We will talk more about this diprotic acid in later lectures. For right now, we'll concentrate on monoprotic acids. Unless you're told that otherwise, that a particular acid is strong, you should assume that other acids are weak. Now let's consider the issue of the equilibrium constant for the dissociation of the acid. Alright, you know that a strong acid like HCl goes quote-unquote all the way to the right, completely dissociates. In fact, Ka for this reaction is 1.3 times 10 to the 6. Notice that the H+ and the Cl concentrations are in the numerator of this expression. HCl concentration is in the denominator. This number is very large, so we have large concentrations of H+ and Cl and very small concentration of HCl. The math tells you what you already know. This reaction goes essentially all the way to the right. And as you saw back in Unit 1, we can assume that the H+ concentration is the same as the molarity of HCl. In other words, all the H+ comes from complete dissociation of HCl, and we don't have to worry about small contributions from the onto-ionization of water. Alright, let's consider a weak acid. We know that acetic acid is a weak acid. It dissociates into H+ and the acetate ion. Now, your general chemistry 1 knowledge tells you that the equilibrium in this case favors the left-hand side. And in fact, the equilibrium expression has K equal to hydronium times acetate over acetic acid concentration, and that is 1.8 times 10 to the minus 5. So you know the numerator, terms in the numerator or factors in the numerator, H+ and acetate concentrations will be small compared to a large denominator, a large acetic acid concentration. Alright, now you can use type 2 equilibrium problems to determine the pH of solutions of weak acids if you know the value of K. For example, at equilibrium, what is the value of H+ in a 1 molar acetic acid solution? Alright, now this is a hypothetical situation in which we take pure acetic acid and add it to water to make a 1 molar acetic acid solution. We'll make a familiar assumption here. We'll assume a hypothetical non-equilibrium condition in which there is no H+, there is no acetate, we have 1 molar acetic acid, and the reaction has to go to the right until Q equals K, or until equilibrium is achieved. If you like, you could stop the presentation and attempt this problem. Alright, Alright, so again, we're assuming the acetic acid is undissociated and the reaction goes forward to the right until equilibrium is reached. Alright, so our initial concentrations of H plus and acetate are 0. Because of stoichiometry, they is increased by X, and the equilibrium concentrations are then X for each of these. Now, our initial concentration of acetic acid is 1. Right, and remember that this concentration appears in the denominator of the equilibrium expression. Well, if there's some increase in concentration of these two species by X, the change in concentration of the acetic acid must be minus X, and 1 minus X is the equilibrium concentration of the acetic acid. In this case, Ka is 1.8 times 10 to the negative 5 is hydronium times acetate over the acetic acid concentration. We insert the value of X for the terms in the numerator and 1 minus X for the term in the denominator. We're going to assume that since K is small, 1 minus X will be roughly equal to 1. That makes a very simple expression to solve. We end up taking the square root of both sides, and we arrive at a value of 0.0042 for X, which remember is the concentration of H plus and of acetate. Alright, this is basically what we need to finish the problem. X is small compared to 1, so we don't need to worry about 1 molar acetic acid. We can proceed, well, we don't need to worry about 1 minus X. We can proceed with the solution we have, which is 0.00042. pH is the negative log of 0.00042, or 2.4. Alright, this is opposed to a strong acid, 1 molar strong acid, where we saw in the previous lecture would have a pH of lower pH of 0. This sort of information is often expressed as the percent ionization of the acid. The percent ionization of 1 molar acetic acid is moles of H plus over moles of undissociated acetic acid, which is 1, and that's equal to 0.42% in this case. Alright, attempt this problem. What is the pH of a 0.1 molar benzoic acid solution, given this Ka for benzoic acid? And here is the reaction that corresponds to that acid constant. Right, again, initially we assume 0 concentrations of H plus, and benzoate is the name of the anion in this case, and these increase by X. The benzoic acid concentration is initially 0.01. It will decrease by the amount X, giving 0.01 minus X is an equilibrium value. If we assume 0.01 minus X is roughly 0.01, then 6.5 times 10 to the negative 5 equals X squared over 0.01 minus X. Simplifies to 6.5 times 10 to the negative 5 equals X squared over 0.01. Gives X is 0.00081. X is sufficiently small compared to 0.01, which would be precise to the hundredths place here in terms of X. And then we can find a pH value of 3.1 or 3.09 for this weak acid. Alright, what happens when X isn't small enough? We see two problems now where it is. Alright, we're going to consider a 0.001 molar acetic acid solution, and while we're at it, we're going to find the percent ionization. Alright, again, here is the reaction. This time it's written in hydronium form, just for practice. In other words, H plus, not H, appears. Notice the equilibrium expression is essentially the same, i.e. water does not appear. We have hydronium and acetate in the numerator, and acetic acid in the denominator. And the initial concentrations of H plus and acetate are 0 and increase to X. And the initial concentration is 0.0010 versus an equilibrium concentration of 0.0010 minus X for the acid. Alright, assuming X is small enough essentially means assuming X is 0.0010 minus X is essentially the same as 0.0010. X is very small. And then, here we will see that this is called successive guesses. If we solve for X, X is 0.00013. Okay. Now we know X is not small enough, unlike other cases, because changes in X, 0.0010 and minus X, minus 0.00013 is 0.00087. Which is not within the uncertainty of 0.0010. In other words, this would round to a different value than 0.0010 if we use the correct number of significant, if we use the correct number of significant figures, I should write this 0.0009. Alright. So X is not small enough because 0.001 minus X, 0.010 minus X is 0.0009, which is not the same as 0.00010. Alright, use the addition rules, a significant figure here. Still, we can use this X value as a first guess. In other words, let's take this and attempt to again solve for the correct value of X. We're going to plug 0.00013 into 0.00010 minus X in the denominator. Alright, so the numerator here looks the same, but our first guess for X appears in the denominator. Alright, this gives X squared over 0.0009. If we even if we keep X to two significant figures, 0.00013 is a good guess. Well, repeats, which means we could treat this as our value of X. To finish, we plug that into the pH expression and arrive at a pH of 3.89. Percent ionization is again the amount of HC2H3O2 that reacted over the total amount, or 0.00013 over 0.00010 times 100%, or 13%. Alright, now let's consider the issue of weak bases. From General Chemistry 1, the most famous weak base is NH3, or ammonia, which reacts with water to form NH4+, ammonium, and hydroxide. Kb for this base is small, meaning that the left-hand side of this reaction is favored. Alright. Now let's consider finding the pH of a 0.20 molar ammonia solution. Given this Kb and this concentration, you should be able to set up an ice table and solve this problem. The approach is essentially analogous to that for weak acids. You assume an idealized case in which you start out with pure 0.2 molar NH3, then the reaction runs to the right until equilibrium is established. Alright, so the ice table for weak base. The equilibrium expression is ammonia times hydroxide over ammonia. Notice water does not appear since it is the solvent. Alright, we have an idealized start on the favored side, which is the left. Initial concentrations of ammonium and hydroxide are 0, increased by X. Concentration of ammonia is 0.2, decreases by X. Equilibrium concentrations of the ions are X, related by stoichiometry, and ammonia concentration is 0.20 minus X. Alright, assume that this is X is sufficiently small to treat this like 0.20. Solve for X, and X is 0.00019. Remember, this is the hydroxide and the ammonium concentration. Alright, we're asked for the pH of this solution. We could take this hydroxide concentration and solve for an H plus concentration now, using Kw equals H plus times OH. Or we could use the approach I show here, which is to find the pOH. Negative log of 0.0019 is 2.72. pH of 14.2 minus 2.72 is 11.28, indicating a basic solution. Note that if you want an H plus concentration, you can always take the inverse log, or 10 to the negative 11.28, and arrive at 5.25 times 10 to the negative 2. Alright, so we've seen in this presentation that acid constants are called Ka, and constants for the dissociation of the weak base example we looked at has been called Kb. Analogously to pH or pOH, it is possible to define pKa and pKb as the negative log of Ka, or Kb. For example, pKa for acetic acid is 4.74, and we have the same Kb for ammonia. Alright. Ka increases as the strength of an acid increases, which means that pKa goes down. Kb increases as the strength of base increases, which means the corresponding pKb goes down. For example, formic acid has a pKa of 3.75. Ka is 1.8 times 10 to the negative 3, found by taking 10 to the negative 3.75. Note that Ka for this is larger than Ka for acetic acid. However, there is a smaller pKa than the pKa of acetic acid. Often when you look in data tables, you will find tables of pKa and pKb instead of Ka or Kb. This concludes the lecture for Module 2 of Unit 5.